TCA cycle has these products where we've got 3 NADH. How much ATP is 1 NADH worth?
Is it 1 for 1?
That's a good guess. It is not.
Okay.
So here's another question. Which B vitamin is NAD?
B3. No.
Excellent. Now keep that number and tell me again how many ATP is an NAD worth?
I don't know. 2.7?
3.
Almost 3?
2.7, almost 3. Exactly what you just said. So each of these are worth 3. So we get 3 NADPH, or NADH, excuse me, times 3. That means we would get a total of, here's our final column, 9 ATP from that. So these are ATP locations. All right, next we get 1 FADH2. Which B vitamin is FAD?
B2.
Excellent. And therefore, how many ATP?
2.
Yes. Basically 2. And we have 1 of these, and there are 2 ATP each, and so we get 2 from there. All right. Then we get 1 GTP. How much is a GTP worth? And it's okay if this one's like...
Isn't that 1 for 1?
Yes. Excellent.
Because that can be GMP and GDP, right? Just like ATP can be ADP and AMP.
Mm-hmm.
Cool.
Yep. So we get 1 GTP, which is basically an ATP. Very similar. And so we total all of these together. 9 plus 2 plus 1 equals 12. So that is how many ATP we would get from 1 cycle of the TCA cycle. Okay? And in real life, we don't get perfect numbers like this, and so it's actually 10 to 12. And so a good rule of thumb is whenever they ask you, and if they're offering a range, take the number that you've memorized and then reduce it a bit and make that the range, rather than increasing it a bit and making that the range. So if 12 is the ideal number, you know it's got to be a little bit less.
Okay.
Up to 12. So anytime they give you a number, just put up to next to it, and then you're good for real life. All right, so now that we've hit products, just watch for those products as we go through the TCA cycle itself. Okay, we have, I always like to start from glucose. I have a sweet tooth. And there's the invisible bloodstream, okay? We're going to be royal today with blue blood. All right. Royal. All right. So glucose, glycolysis, we do that whole thing, and then we end up with pyruvate. And then pyruvate is where we're going to have pyruvate, the pyruvate dehydrogenase or decarboxylase. I always forget which because it's like it's doing both, but it's a complex, and that makes us into acetyl with a T, acetyl-CoA. Now acetyl-CoA has 2 carbons, and that's what I'm drawing in circles off to the side here. And it is very, very helpful in the TCA cycle to keep track of carbons, because if you can keep track of carbons, it makes other concepts make more sense later, as well as giving you a, okay, I know that this has 4 carbons, therefore it can only be these molecules kind of a thing. Okay? So, acetyl-CoA, let's go inside the mitochondria. We will have a blue mitochondria today. There we go. That's our mitochondria. Mito. Okay. So acetyl-CoA with 2 carbons is going to join a molecule known as oxaloacetate, abbreviated OAA for obvious reasons. All right, oxaloacetate has 4 carbons. So if we add 2 and 4, we're going to end up getting 6. And the first guy that we're going to get, the 6-carbon molecule, is citrate. Okay? Now, with citrate, we will hit the enzymes on the way back. So right now we're just going to do molecules. So citrate next is going to be isocitrate. And I like to, so far, pair these where we have oxaloacetate and acetyl-CoA. Those two, I like to remember the number of carbons. Acetyl-CoA is like the linchpin molecule, and it's probably one that's pretty good in your head because you've had a lot of pathways that hit it. And then oxaloacetate, I just like to have these two paired. When I think of one, I think of the other. So we have one pair, the formative pair. The next ones, they're the pair of oranges, basically, is how I always think of it, because it's citrate and isocitrate. And oranges. All right. Okay. And I wish I had an orange marker, but I'll use this. So we're just going to draw a couple oranges over here. And then there.
Do you want an orange marker?
Oranges. That would be great. Or a magnet to keep my orange up here. All right. Fantastic. And so, like with anything, breaking it up into smaller bits makes it much easier to remember. So far we've got 2 things to remember, and those 2 things give us 4 things. Formative pair, 4 plus 2, acetyl-CoA and oxaloacetate, and then the 2 citrate. Now, after that we have alpha ketoglutarate. Okay, so following alpha ketoglutarate, and by the way, keto, ketones, and there's a ketone formed in this, and that's why it's called ketoglutarate. And a ketone is a double bond to oxygen found in the center of, or at least not at the end, on any of these inside carbons, any of these 4. A double bond oxygen coming out from one of them would be called a ketone.
Yes.
Okay, and so ketoglutarate. Okay, and there are 5 carbons at this point because we lost one right here. Okay, next, after the alpha ketoglutarate, we have succinyl-CoA. And after succinyl-CoA, just because they go together, and then we'll do these 3 together really quick, is succinate. Succinate. Okay, so with this one, I like to have a picture. We've got the 2 oranges. Now we're going to have a jar, a glue jar at your grandma's house. And this is where she keeps suckers. It's an old glue jar. Okay? And one of those suckers has a CoA stuck on the side, which is just 2 molecules, and the other one doesn't. Okay, so you got 2 oranges, and then you've got the glue jar, alpha ketoglutarate, and 2 suckers, succinyl-CoA, succinate. All right. After succinate, we have fumarate, and then malate. And for this, I just think of a radio, an FM radio station playing on a radio. If that helps. All right, FM. Fumarate and malate. Oh yes, and the radio is smoking a little bit because it's fuming. It's a very old radio. So now that we've got the pictures out, I actually see these pictures, you can see them on just at your grandma's house. You go in, and going in the front door is linked to acetyl-CoA and oxaloacetate, because the doorknob makes me think of a single carbon because it's round. That one's the loosest one of the bunch. And if you would like to modify it, go for it. Then we go to Grandma's table, where she has a platter. There are 2 oranges on the platter, which represents citrate and isocitrate. And then there is, at the other side of the platter, so if the oranges were on the top left, then on the bottom right maybe, you have a glue jar with 2 suckers sticking up. Alpha ketoglutarate, and you can stick an alpha symbol on the glue if you want, so you start with that. And then succinylCoA and succinate. After that, and then off to the side from the platter is just the radio, your grandma's super old radio, the FM radio that is totally busted, except it's not quite stopped with the FM station. So then you have fumarate and malate. And then that gives you the molecules. So let's go ahead and run through. Go ahead and close your eyes, and you can do it out loud or in your head. And go ahead and see if you can go.
So when we're keeping track of carbons, acetyl-CoA has 2, oxaloacetate has 4.
Yes.
And they come together to make 6 in citrate.
Mm-hmm.
Isocitrate is just changing the formation.
Yes.
And then after it turns into isocitrate, it loses a carbon.
Exactly. And so alpha ketoglutarate then has
5 carbons.
5. How
many does succinyl-CoA have?
To be honest with you, I don't remember where the other. Yes, I'm pretty sure that succinyl-CoA has 4. I think the carbons come off one after the other.
Okay. And then should we keep track of carbons with succinate and fumarate and malate?
The rest of them are just 4 carbon molecules. Really, the most important thing is to remember that most of these are 4 carbon molecules, and the reason that that's important is when it comes to amino acid metabolism. Why can we use some amino acids for glucose and not others? Why can we use oxaloacetate from amino acids but not this oxaloacetate? If we use this oxaloacetate, we can't replace this 4 carbon molecule. If we use up all the 4 carbon molecules here and then they're all gone, well, we can't use acetyl-CoA to make glucose because there's no one to pair it with. That's the really big important thing. The details of how many carbons is not as important, but usually when you learn all the details and then you forget half of them, what you keep is oxaloacetate has 4 and acetyl-CoA has 2. That's the actual important carbon numbers.
Okay.
Yeah, but it is good to know just because then you layer the knowledge and it sticks longer for the actual important stuff at the base.
Cool.
All right, and how'd it go?
Good.
Excellent. Okay, so next, we have some enzymes that we'll throw in, and enzyme the first, citrate, or that thing. This is an arrow pointing to citrate because it's just that thing. Citrate synthase. And that just kind of makes sense because you would make citrate with citrate synthase because it synthesizes it. Next, isocitrate. This is an off-brand orange, apparently, because it looks the same, but it's not, and so someone conned you into having this orange. All right, so this is aconitase. Aconitase is the enzyme used here. Aconitase. Okay. Next, we would have Isocitrate Dehydrogenase. So I'm going to say that thing dehydrogenase. Yeah. Goodbye, carbon. That thing, dehydrogenase. And if we have a dehydrogenase, what do we know?
We're losing a hydrogen too.
Yes, and that hydrogen has to go onto?
An NAD.
Exactly. And so we make NADH, our first one. Go team. All right. And moving from there, alpha ketoglutarate is what is formed, and alpha ketoglutarate going to succinyl-CoA is going to be alpha ketoglutarate dehydrogenase, or is it succinyl-CoA? All right. I am going to, yeah, that would be great.
Alpha ketoglutarate dehydrogenase.
Awesome, thank you. Okay, so we have 2 dehydrogenases in a row, is how I should have remembered that. And how you will. Alright, so we had a pair that were citrate related, then we have a pair that are dehydrogenase related. And then coming off of succinyl-CoA, the enzyme between succinyl-CoA and succinate is going to be Succinyl-CoA synthase. But you'll notice we aren't making succinyl-CoA right here. And it's synthetase, excuse me. We are actually taking succinyl-CoA and turning it into succinate. So we're using this enzyme backwards, if you follow my meaning, from the way that it's named. Yeah. And it's synthetase, as you can clearly see through my handwriting. So what do we know that synthetases usually take?
ATP.
Yes. And in this case, a GTP. And since it is running in reverse, we're not spending one, we're gaining one. So this is our GTP. Plus GTP. All right. All right, so from the succinate to the fumarate, if you would double check, I believe that it's succinate dehydrogenase.
Yes.
Okay, and does this one make, what kind does it make?
Makes FADH.
Okay.
Which is nice because it's going into the F.
Oh, sweet. I'll always remember that now. All right. And so this one is FADH2. Okay, so, and the 2 weird guys are next to each other. Okay, because GTP and FADH2 are the 2 that are odd. All the rest of them are NADH. Okay, so with the enzymes, I'll do this one with you because it's rusty. Go ahead and find the first pair. So you're at grandma's and everything, and you can see, go ahead and see the oranges, and then just say, okay, there were 2 enzymes for oranges, and what were those 2 enzymes now? And that was citrate synthase, and then aconitase. Because one was an off-brand orange. And then next, we have the glue jar trio, and the first 2 of those are going to share something. Do you remember what they share? Because we have another pair. With the enzymes, it's in pairs.
That they're dehydrogenases?
Exactly. And so then you know it's that thing and that thing dehydrogenase.
So alpha-ketoglutarate dehydrogenase.
Mm-hmm.
And Succinylcholine dehydrogenase.
Exactly. And then for the next pair, what does this pair have in common? Or whatever?
They're backwards.
They're both weird, yes. So backwards, weird, yes. Backwards is for the first one, and then weird is for both of them.
Okay.
So if we were pairing the enzymes. So the backwards one gives you what?
We use Succinate Synthase, or Succinylcholine Synthase.
There you go.
To make succinate, and we get a GTP.
Good. And the next guy?
That's Succinate Dehydrogenase, and we get an FADH2.
Excellent. And then that's how far we got.
Cool.
All right, so we've gotten 3 pairs, and then the only thing that we have left is between fumarate and malate, and then malate to oxaloacetate. One of those has a dehydrogenase. I believe that it is malate dehydrogenase.
Mm-hmm.
And then right here you have like fumarate lyase, I think.
I just have fumarase.
Fumarase, okay. So fumarase and then malate dehydrogenase. All right. So the way that I'm at least going to do this presently is I'm going to stick an ace of spades, because I actually memorized this part without pictures, which is why it's gone. All right, I'm going to stick an ace of spades underneath the radio. And then I'm going to make so that this stuff that's off-gassing, that's hydrogen. So I know that it's the dehydrogenase above. It's hydrogen gas coming out of the radio. I'm so sorry, Grandma. No wonder your voice is so high. That's helium, but there you go. All right. And so that means that if we were to write it in, this is going to be fumarase and then malate dehydrogenase. And we know that this is going to give us our last NADH, because we've already used up the 2 weird guys. And then that is the entire Tca cycle, also known as the citric acid cycle or the Krebs cycle.
Or the cycle. Or the cycle?
The cycle, yes.
Yeah, I have a lot of teachers call it the cycle.
That's awesome. I haven't heard that one actually. The cycle. That would be so much more friendly. All right, it's the cycle now. So, cool deal. Now we'll move forward to electron transport chain. So, did you want to go over all this one more time to make sure it sticks, or are you good?
I think I'm good. I think I'll repeat it later tonight.
Okay, you guys pause. All right. And good to get rid of it?
Mm-hmm.
Okay. Okay, mitochondria again, because this is still inside the mitochondria, and I'm just going to draw the Tca cycle right here in mini Tca. Happy face. All right. And we get from the Tca, without looking, how many NADH?
3.
Good. How many FADH2?
2.
We actually only get 1 of those, but it is worth 2 ATP.
2 ATP.
So that's where the number's coming from. And then what's the last guy that we get?
GTP.
Awesome.
And we also only get 1.
Exactly. So all of these guys, the GTP, frankly, just goes and is like, I'm a GTP, I'm good. He doesn't need to go to the electron transport chain because he's already usable. The electron transport chain is going to have a few complexes. And what's the best way to draw these? All right. We will go ahead and have complex 1, complex 2. Complex 1 will take the NADH buddies, all right? And complex 2 will take the FADH2 which is nice. These guys will then send electrons to complex 3, which I should not draw right there because that's where you have the carrier, dude. All right, to complex 3 over here. And they will send them using coenzyme Q. And this is going to carry electrons over to the third complex and deliver them. And double check this, but something that you will want to know is which of these actually will pump hydrogens across. And as I remember, this is something that you need to verify though. Hydrogens will be pumped across by number 1 and number 3 and number 4, basically just not number 2. Okay? And now number 3 is going to use a cytochrome C, to move the electrons to the 4th complex. And the 4th complex is also known as ATPase, or the ATP pump. And this is the hydrogen ATP pump, and it's going to take all those hydrogens that have been built up across the membrane, the matrix. And then those are going to shoot through this 4th complex and generate ATP, literally like going through a turnstile, how you push through at the train station, you push through those rotating things. That's actually basically what this looks like, and when things push through, they generate energy. So it's an energy efficient translation. So, now, the hydrogens are being stored. I should have mentioned that up here, all the hydrogens that you're pumping through are going to be stored in, you know how the mitochondria has a double membrane, yes?
Yes.
Okay, so you load up a ton of hydrogens in, I believe it's the intermembrane space. And then those are going to shoot across. Once you've loaded those up, then they can go through the ATPase pump, and they will shoot across through it, and that will generate it because of a gradient. Make sense? It's possible that it's flipped. I'm a little bit rusty on the ETC. Do you have it available for us to double check so that we can?
Yeah, I have it right here.
Okay.
It's kind of, I don't know where to download it, so it's.
It looks like it's all right. So
yeah,
down a little bit. So complex 1 has 2 hydrogens and uses iron. And then complex 2 does 0 hydrogens like we said and uses iron. And complex 3 uses coenzyme Q to move the hydrogens and electrons from 1 and 2 to itself. And then we have cytochrome C moving copper. Okay, that was the one thing. Cytochrome C uses copper. The rest is iron. Okay, that'll come up in nutrition. So, all right. And intermembrane space versus matrix. Okay, so it's actually the other way around then. So the hydrogens get loaded up into the matrix, and then they shoot through to the intermembrane space to generate the ATP. So in this picture down here, we've got hydrogens being loaded up here and through this as well. 2 here, 4 here, 2 here, And these two guys are iron, 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 and copper was right there. Okay, anyway, all the hydrogens are being loaded into matrix up here. Matrix. And then down here is intermembrane space. And that kind of makes sense because it's easy to keep this smaller location at a lower concentration and shoot them in than it is to keep the matrix at a lower concentration where you have so many reactions using hydrogen going on.
Right.
And it's a bigger volume. All right, and then that is the electron transport chain.
Okay.
Yeah. Any questions?
I don't think so.
Okay. The important thing to remember, I would say, is, or an easy way to remember, rather, is I like to split it 1 and 2, send them to 3 using coenzyme Q, and so you just make this triangle right here, and I actually usually include 3 right here, but whatever. So 1 and 2, just give them to 3, and with a little picture graphic, that's easy, and then 3 uses cytochrome C to send them over here. So I'm going to redraw it so it's pretty for memory, now that I actually can pull it. Alright, so you've got 1, 2, 3, and then these guys send like this using Q, and that's really easy. That's part 1. Part 2 is C, or cytochrome C, to go to number 4. That's the electron transport chain in stick figure style. So, yep, part 1, get all the electrons and or hydrogen. This guy technically, this is something that she's not going to ask you probably. You never know with Professor Homi, but I don't think so. This guy's sending electrons. This guy's sending hydrogens, which is why this guy doesn't have any hydrogens moving anywhere. It's like, why are you not doing any work? It's because he's actually sending the whole hydrogen to complex 3, whereas this guy's just sending electrons. And then complex 3 will take the hydrogens and deal with them. And so this guy does hydrogens, and this guy does hydrogens, and then this guy will shoot hydrogens the other way since I flipped which way we're looking at it. Anyway, so yeah, and then they just get sent over. All right.
It kind of rhymes. 1 and 2 use Q, and 3 uses C, 3C to 4.
Nice. I'll keep that.
I like rhymes when they sound like they go well together.
As long as you also like limex.